Hi, everyone. I'm Mike Kalber, a partner solution architect with AWS. You saw my partner, Anupam Mishra. He's a principal solutions architect with AWS. Today, we're going to be talking about optimizing Redshift on AWS. And at the end of my slide presentation, Anupam will give a demonstration to show kind of what those best practices are in the real world. So a quick overview, like I just mentioned, we're going to do a very high-level overview of Redshift, the typical node architecture, and then we'll hop into the optimization tips, then the demonstration, and then hopefully we'll have enough time left over to do question and answer for you guys. This is just some of the customers that we have that are using Amazon Redshift. One I want to call out specifically is Foursquare. Foursquare had an issue a while ago where they wanted to kind of have a cost savings with their existing database system. So what they went to is Amazon Redshift. What the problems that they had was they had yearly licensing costs with their existing database system, and it was very hard to keep up. So they had to have a dedicated staff to sit there and maintain it, and they wanted to kind of shift those people to kind of a different area and use their time a little more optimally. So what they did is they introduced Amazon Redshift, and in conjunction with Amazon Redshift and Tableau, they were to get those cost savings down in terms of not having the licensing costs anymore, and they could get the team to focus on other things in terms of optimization and other projects that they wanted to push forward. Now we'll just start with a quick service overview of Amazon Redshift. Amazon Redshift is our fully managed data warehouse, simple, cost-effective SQL, using standard SQL, and you can use your existing business intelligence tools. No upfront costs. There's also Amazon Spectrum, Amazon Redshift Spectrum, which we'll be showing a demo later, where you can query petabytes of data across S3, and it supports formats like CSV, Grok, Parquet, and other formats that you can see on the Amazon Redshift website. And then this is just a typical node architecture. So there's two important parts to the Amazon Redshift cluster. There's the leader node and the compute nodes. The leader node, obviously, as it sounds, is the leader. It orchestrates the communication between the compute nodes. It parses and develops the execution plans to carry out the operations and sends those optimized query plans to the compute nodes. And the compute nodes are the ones that actually do the data crunching. So there's two different types. There's dense compute and then dense storage. The DC2s, I don't know if you're familiar, just launched in October as opposed to the DC1s. So I think it's 30% more performance at the same price. And then this is just another example of leader node showing how it's partitioned and sending the data to the compute node. So the compute nodes have slices. So for example, a DC2 large will have less slices than a DC2 8XL, and you have to choose how many slices you want based on your workload. And not one size fits all, but it just depends on what you're doing and your cost savings and stuff like that. And then we're diving right now into the optimization part of it. So the first part is we want you to load your data efficiently. So when you're using the copy command, once you load all the data in parallel. We highly recommend compressing the data. If you guys use the copy command, by default, it will use a default compression and thus load the data a little more quickly. Sometimes the default compression isn't optimal, so sometimes you'll have to use, analyze compress and play with a sample set of data to see which compression algorithm works for your data. And then obviously we want you to split the files into multiple files so that you can leverage the parallel processing of the slices and the compute to input or to slurp up that data. Next, we have table design. Upfront table design is critical. The distribution key and sort key obviously influence performance. Primary key, foreign key, unique key. The unique key constraint is not enforced. Data distribution has two primary goals. Those are distribute the workload uniformly and minimize movement. Data movement during a query. And then also we want to compress data for faster speed and lower cost because you don't want uncompressed data on the disk because that's obviously more expensive for you to spend. Next, we'll talk about sort keys. So with sort keys, we want to use these on where clauses. This is just, sorry, one second. Did I skip something? No. This is just an example of the sort keys. This is just a little more data, different types of sort keys and where they're most applicable. Compound sort keys are good for known query patterns like time series data. Interleave sort keys give equal weight to each column in the sort key. The interleave sort key is also good against very large tables, for example, something with 1 billion rows. And then this is just an example of how you can see uneven distribution keys just visually. So with uneven distribution keys and the data being unevenly distributed across your nodes and slices, you're going to have pretty bad performance if one slice in one node is taking longer, because you're only going to be as fast as your slowest slice. So that's why we stress making sure up front that you have the right distribution keys to get that data evenly distributed across your nodes and slices. And then this is just some of the optimization you can do for the skewed distribution. There's a GitHub repo with some scripts that I'll share at the end of the slide that has various tools and automated things you can run against your Redshift cluster to optimize it. So when choosing when choosing distribution key, you want to make sure it has high cardinality, so that's something that's rather unique. And the values are very uncommon. So for example, if you can't find a distribution key that's a good fit, you can try using even. And what even distribution key does is it distributes the data across all the nodes evenly, basically in a round robin style. And then there's also another option for smaller tables where you can use distile all. And if it's a small enough subset, that will put it on the first slice of every compute node, so that it doesn't have to go out and get that data to another node for something that's, that you would query a bunch or join. Next thing I want to talk about is Var Columns. Some of the best practices we have there, some people think that it's best practice to use the maximum size just so you don't have to do anything later. Use the smallest possible size you can. We compress data pretty well in Redshift so that you don't have to worry about the large size. It has minimal impact on the size of the data tables. During processing for complex queries, however, intermediate queries need to be stored in temporary tables or potentially on disks. So if you have larger Var columns, they're not compressed, so it can use that disk, thus slowing down your queries. So like I said, you don't want to use the largest Var column you have. You want to use what makes sense for you guys. Next, we have disk-based queries. Obviously, disk is slower than memory. So there's a script or a query that I've written up there that will identify any of the queries that you have that are disk-based. And obviously, you want to optimize those and make sure that either increase the memory in the WmQ, which I'll talk about a little later, or maybe it's just not an optimized query and you can take a look and see to optimize it. There's also queue assignment rules that I just mentioned. And then there's dynamic memory allocation you can do, so you can increase memory on specific queues for specific sessions. If you have a end-of-year report or end-of-quarter report that's using more resources than necessary, you can kind of tweak that on the fly without having to restart the cluster. You can also add new queues to WmQ. The only problem is if you add a new queue, you'll have to restart the cluster. And then next we have the commit queue usage. So the commit queue usage are expensive. There's a script that we have called commit stats SQL. You can run it and it'll show various queries and how long they've spent in the commit queue. And then you can analyze that and see what you need to do to optimize it in terms of is it loading data too long? Are you pulling from the wrong data source? And then this is just an example of what the script looks like. So you'll see this is just the query that you see up there. It just shows the commit time. It's not necessarily the prettiest thing, but you can see which queries on which nodes are taking the longest, and then kind of dig into what's going on those. And next I'll talk about the WmQ. So there's two queues created by default. There's a super user queue. This is only when you want to run queries that affect the system or for troubleshooting purposes. And then there's a default user. The default user queue is initially configured for 5 concurrency, but you can You can tweak that depending upon your workload. I don't remember what we recommend, but it depends on your workload. I think we had at one time said we didn't want to go over 20 for concurrency, but it just depends on your workload. And then again, with the WmQ, you want to identify short and long-running queries to prioritize them. Obviously, the shorter ones you can schedule around the long-running queries, like I mentioned, the end-of-year reports, the quarterly reports, those types of things. And then there's another script that I just mentioned to tune peak concurrency. So it's a script that you can see to make sure your queues are configured properly, where you're not running into collision and waiting for stuff to queue up. It's listed here, and I have another link at the end of the slides to show where you can get the files and the tools to kind of look at the queues to make sure you've scheduled everything properly and set up the queues properly. And then this is just an example of a WmQ and how it works through the process. So if a user is logged in as a super user and runs a query, the query group label is super user. The query is obviously assigned to the super user queue. And then if a user is assigned to a listed user group, it's assigned to the query, the queue that is assigned to that's assigned to that user group. And then if it doesn't match anything, it just goes to that default queue, and it's executed across the Redshift cluster. Next, we have table maintenance. With table maintenance, like other databases, requires statistics about tables and composition of data blocks being stored in order to make good decisions. So we recommend, depends on your workload, analyze to get those statistics updated and so that the leader node can optimize those queries for you across the compute nodes. And then you also want to run analyze when loading popular columns. And then vacuum is another one. So when you delete rows or add rows, there's unnecessary space that's there. So you want to use vacuum to kind of reclaim that space. So if you delete, like I mentioned, if you delete rows, it doesn't really delete them. There's empty space in there, so that's just empty space that you can reclaim using the vacuum. And again, vacuum tables, there's a script that's there that will, based on threshold, you can configure to say if it's over a certain percentage to run that, to run a vacuum against it. And you want to run it off hours because that could potentially cause issues if it's a long-running vacuum query. And again, these are all just kind of common things I've seen customers use. It depends on what your workload looks like to kind of really tune the vacuum and some of the maintenance stuff, off hours, make sure it doesn't collide in the maintenance window, and make sure it's not blocking other queries from running. And with that, I'll turn it over to Anupam for the demo.
Thanks, Mike.
Yep. There you go.
Hi, everyone. Great recommendations by Mike. So let's put some of those things into practice. A lot of things which Mike talked about are how to optimize your Redshift cluster. But last year, we announced a new product called Redshift Spectrum. How many of you are aware of Redshift Spectrum? Just raise your hands. Oh, great. How many of you use it in your work, or probably one or two? OK, awesome. How many of you use glue here? 3 or 4, yeah, OK. So what I'm going to show today is how Redshift Spectrum can be used to combine the power of Redshift with the free-formed queries which you can do on S3. So traditionally, the way data warehousing world works is you have some data coming into either your S3 or your databases through various import jobs. And then it goes into, there's an ETL pipeline which puts it into Redshift, and that's where you query. And there were 2 parallel paths earlier, like Redshift was one path and querying S3 was one. But with Spectrum, both of them combine together. And you can query your S3 files from Redshift as if the data was stored in Redshift, even though it is not stored. So you're directly sending your queries to S3. And I'm going to show you how that works, and also share some best practices when you work on a use case like that. How can you optimize those use cases? So let's jump into that. Awesome. So I'm going to use my browser. Cool. So first thing, what I want to do is I want to start with the Redshift cluster and show you what are the different things we can do with Spectrum and how do we start using Spectrum. So let's put that to use. So first I'm logged in into my AWS console. I've already created a few databases, so I'll use one which I have not used before. I created a bunch of test databases, so I'll probably choose 501 to start with. And then I'll take the endpoint and try to log in into this or connect to this. Okay, so I already have pSQL here, so which allows me to send queries from my console to. Okay, hope this is visible. Yeah, I think. Anybody not? Should I increase the font size or pretty good? Pretty good. Awesome. So let's connect to this database. Okay, so we are in our new Redshift 501 database now, our data warehouse. What we want to do is, first thing, I want to check what version it is. So I've created a list of scripts which I'll be running, and also explaining you what each one of them is doing. And by the end of this exercise, you will know how Redshift and Spectrum work together, how you can create automated pipelines which create Parquet files, how do you compress files. So if you want to just take the gist of it, there are three things which you want to do when you are dealing with files which are being queried. So you're talking about S3 files. One is you want to compress the data. Second one is you want to have a columnar storage. So there are a lot of formats. We are going to use Parquet for today. And then the third piece is making sure you keep your data partitioned so you don't scan the whole storage. Those are the three things. I'm going to show all three of them step by step, and hopefully you'll make some good use of that. So first, we have checked the version. Spectrum is supported only above a certain version. So it's 1 point, let me increase the font size of this as well. OK, awesome. So 1.0.1294. If you upgrade your Redshift to above this, then you can use Spectrum. Otherwise, it's not allowed. So with that being clear, let's go with a sample data set which I have here. So and increase the font size here as well. OK, let's make it a little smaller. Cool. So I'll make it a little shorter. Awesome. So what I'm doing is I'm going to a S3 bucket and checking what data I have in this folder. There's a folder named ticket spectrum sales. So there's some sample data which we have. It's called sales data. I've already downloaded this file. So what I'm going to show is how this file looks like. I'll just look at some of the top records of this file. Yeah. OK, so if you look at it, there are a bunch of numbers here. Like, it's hard to make a sense of what these numbers mean, but you can assume it's a tab-separated file with a bunch of columns, and each column probably has some meaning. So given this data in S3, what we want to do is we want to query this data using Redshift. So this is the data sitting in S3. How do we query this file? You can have a CSV instead of this. You can have a log data which is generated by your Apache logs or something else. So next, what we're going to do is we're going to create a schema. So apologies for having _5 here. I was doing a lot of experiments, and I kept changing the number, so we reached number 5. I hope my demo will work. So let's start with creating a new schema. So my schema got created. It says create schema is successful. Awesome. So as you can see here, I'm creating a database named SpectrumDB5, and the schema name is Spectrum5. And then I have a specific role which I have created here. This role has access to S3 as well as Redshift, because this Redshift now needs to go to my S3 bucket as well. So this has both the things. In the interest of time, I'm not showing how to create this role, but if people have questions, I'll show it. Now let's move to the next step. Once we have the schema, let's create a table from the data which we just checked. So I showed you some of the file which we have in S3. So let me create this table here. So just go. Let's quickly go through this statement. So what we are saying is create external table. External table means the file which is not on Redshift. Redshift will assume as if the table exists locally, but the table data actually is still in S3. There's no copying happening here. Nothing is being transferred. It is just a logical statement saying, from now on, whenever somebody refers to spectrum_5 dot sales, this is the schema which we need to comply with, and the data is stored here. So there's a pointer to this file, and there's a catalog which we create for this. So now what we have done is we have created an external table. External table is a text file. It's a tab separated file, and then it's located here. So now let's go to the next step. So now that we have created a table, let's do a simple count star query just to see how many records we have. So that was it. So when I'm firing a count star, what it is doing is it is going to my node, and this node is sending the query to S3. It's checking which file to download, what to do with the file, and then sending the records back. So it's everything which I'm doing here is going to S3 and coming via S3. Now let's do one more statement, a little bit just to see what kind of data we have here. Just showing the top 10 records. So there's a sales ID, list ID, seller ID, and a bunch of things. And because these are the names we gave, we said that the first value which you see in the file is sales ID. The second value which you see in the file is list ID. So we created a schema, and everything in the file now aligns with our schema. So far so good. So we have our schema ready. We have our table ready. Now one of the things we can do here is, let's say when we are doing this, if we do an explain plan of this, you can see it's gonna do a I'm highlighting this piece, S3 query scan. So it's going to S3, it's gonna do a scan there, and then it's telling which file it will go, how many potential rows it's gonna scan. So it's telling you that this query goes to S3 and what operations will be done on S3. Now let's move to the next one. So far we have created a file or created a table which is a spectrum table. It is going to S3. It allows us to query the data from S3 without anything being done on Redshift side. Now let's create a normal S3 Redshift table. So I hope everybody here has probably created a table some other time. So it's pretty simple. I'm calling it an event table. And there are a bunch of IDs here, event ID, venue ID, start time, and few other things. So once we create this, we're gonna check what this file is. Because I'm going to copy data from this file into this. So it's a standard Redshift copy. All of us have done it some or the other time. So this is an S3 file. If I want to do check what kind of things it has, all events, cool. So all events is a file which is which also has a bunch of values separated by a delimiter, and there's no header here. So what we will do is we'll load this data into the new table which we just created. So these are events. So just to give you the context about data, the data which we have in S3 is called sales. So all the sales which have happened are coming into S3. Let's assume there are multiple systems which are pushing the sales data into S3. Now we have created a table called event. Event is just a metadata or a catalog data. So it's telling us these are the potential events we have. One of the best practices here is whenever your data is just a dimension table, it's good to just keep it here, because it's not too much data. So keep your dimension tables here, and if it's fact table, you can put it on S3. Some people also do something called rotate old data into S3. So if your Redshift cluster becomes too big, and you know that old data is not queried as much as I want, you can retire your old data into S3, but it is still queryable. So I'm going to show that piece also. But let's quickly get to this Redshift piece. So we created a table called event. Now we're going to load this table with the data which I just showed you. So it's a copy command. So what we are saying is copy data from this place in Redshift, in S3. And we are telling the time format. We are telling some region where this data exists. It's pretty 10 rows of data, so I think it'll do it quickly. Let's see. And by the time it does it, let's see. Maybe I'll just log in here. Okay. So awesome. So there are about 8,798 records loaded. So there are a lot of events here, and then which are loaded into Redshift. So this is a local table. Even though the data was in S3, we copied all the data into Redshift. So far we have two use cases. Sales data was in S3. It is still in S3, but it is queryable by Redshift. Now we have events data. It was in S3, but we have copied into Redshift because Redshift queries are generally faster than the Spectrum queries. So we have done those two things. Now let's say we want to combine those two together. Like we have some data in Redshift, we have some data in S3. How do we combine them together? Like one of the use cases which I see very commonly is a lot of companies get their access logs, so how people are using their websites, like which IP addresses are using it, which browser people are using, things like that. And that generally comes as a log format, Apache log or some standard comma-separated format. And a lot of companies want to use that data along with the other analytical data they have. They want to see for a specific geography how many people were browsing my website, combine it with a lot of other data you might have in Redshift. So you can do like dynamic queries. So now we have recreated that use case. We have events here and we have sales there. Now let's run a join query. So what I'm going to do next is I'm going to, so before we run this query, let's understand what this query is doing. We are saying select top 10 spectrum.sales.event.id, comma sum of sales.price paid. So what we are doing is we are saying, tell me the top 10 events where the maximum sales happened. So it's going to tell us the most successful events to us. And event data is in Redshift, and sales data is in S3. So, and we are joining them as if they are both local. So we are saying sales.event.id is equal to event.sales.id, and price paid greater than 30. So we are interested only in events or sales where at least $30 were paid to us. And let's run it. So we got our top 10 events where things happen, and as you can see, it's pretty quick. Depending on how you store, I think your query performance will improve or degrade. So far, we have not done much performance things. We have data in S3, we are just using it. We have data in Redshift, we have used it, we are using it. Now let's jump into the performance side. How do we, so far it works, but how do we make it more scalable, more optimized? So what can we do in this use case when you have exabytes of data? So Redshift Spectrum can support very, very large files and a huge number of files. So we can do a lot of optimizations to improve the performance of Spectrum. So let's go through the performance things I talked about one by one. So first thing we're going to start with is partitions. Before I jump into partitions, let me just quickly show the explain plan of this. So you'll see it very similar to the explain plan which we saw before. So let's not look into everything, but I just wanted to show you it's doing a hash join, and it's joining using S3 query scan. So it's again going to the sales, it's doing a S3 query scan, it's doing a hash aggregate in S3, it's telling how many approximate rows it's going to scan, and it will do a S3 sequence scan. So it's just to get an idea. Now, what we're going to do is we're going to create a similar use case, but with partition data. So let's say if we have partitions, how many of you use partitions already? Raise your hands if you use. Okay, so it seems there are a lot of people who have not used it. So the way partitions work is, generally, you have like, in our real world use cases, we have a lot of data. It could be terabytes of data which are stored in file. If you create a single file which has all the data stored in it, and you query through Redshift, what Redshift will do is, first it will download the file, parse it, and then try to make some decisions. So the downloading itself will take a lot of time. In a lot of cases, we don't need to download the full file, especially for examples where you are interested only on a specific date. You are saying, hey, tell me what happened yesterday. You don't want to download the full year if you are interested only in yesterday. So a lot of people partition by date. They'll say they'll have the first partition by year, then month, then date, and then within those partitions you have different files So Redshift will intelligently identify what files I should download, and then it will minimize the data set. So that's where partitions are useful. So now let me show you how partitions can be implemented. So if you have large number of files in S3, or you can, so you can improve the performance of the use cases like this. So let's first look at the data. So there's another data set which I have. First, I'm showing you the data. So I just did a S3 list, and I'm going to a location called Spectrum Sales Partition. So the same data, but it's partitioned this time. So let me show you a gist of how this data looks like. So as you can see here, the first value or the name of the folder which we have is sales date equal to 2008-1. So this is the first partition key. It's saying all the data corresponding to the first of or January of 2008 is going to be in this folder. All the data for February of 2008 is going to be in this folder. So let's look into one of those folders first. So I'll say, that's great, like you have done a good job segregating this, but let's look into what is inside one of them. So within each month, we have 6 files. So it doesn't need to be 6, it could be any number. Maybe you have daily level files, maybe you have files generated every 5 minutes. It doesn't matter, but you have some files, and you want to see, and let's look into one of the files so we understand what kind of structure they have. So I'll do a head, 000. Okay, cool. So I had already downloaded this file, but this looks very similar to the file we saw earlier. It's again a delimited file and a lot of columns here. So structurally it is same, just that the data was splitted into multiple files, and those files are stored in a way such that we know which, for a given date, where are the files for that date. So that's the simple partition here. Now, let's move to the next step. So once we have we know that the partitions, let's go to the next step. So what we're going to do is, we're going to create another table, which is very similar to the first table we created, but let's look at the difference. So we are again saying create external table. We are telling the name of the table. We're defining the schema. And then finally, we are saying fields are terminated. What is the delimiter? Stored as text file. And then this is where my partition data is. And table properties here. So one of the unique things here, which is important to notice, is partitioned by. So when we create a table, we tell the table, hey table, you are partitioned by this specific column. And it could be partitioned by multiple columns, because you can have maybe different product lines, and within those product lines you have different dates. So you can say first product number will come, and then the date will come, or it could be a lot of hierarchical information. But partition by is one of the columns. So you just say which column it is partitioned, or it could be multiple columns. So let's run this. So it created very quick. The same concept applies here. This query doesn't do anything. It's just telling it, hey, the data is stored here, and this is the metadata which we expect, or we call it data catalog. So this is the catalog, and the data stores here. So now we have very similar table as before, just that the raw data is partitioned here. So let's run the similar query here. Right now, when we created this, it has not loaded data. So as if you remember, when we went to this location S3, it had multiple folders. So by default, it has not added any partitions into it. So we will need to add it. So what we will do is we'll say, hey, these are the dates you should be aware of. So what people do is every night or every day or every 5 minutes, whatever the cadence is, every time you see a new data file come, or every time there's a logical interval of partition, you just add a new partition so it knows that this is the partition I need to scan. You can also do it automatically. I think for this example, what I want to do is I will add all the partitions we had, and I'll just jump into one of those statements so we know what it is doing. So let's look. Okay, so it's running some of them, but let it finish, and then I'll. So what it is doing is, let me show you. Okay, alter external table. Cool. So it's finished. So I had like repetition of statements like this multiple times. But let's jump into, let's look into the highlighted section. I'll probably highlight one other one. Let's highlight this one. So what I'm saying is, alter table, the sales underscore part. So we just rename the table to, or created a new table called sales underscore part. Part means partition. And then we are adding a partition, sales date equal to 10, so we are saying October 2008. And then we are saying the location of this partition is here. We are just telling the location. And after that, it knows that this is the data I should be aware of. So we just made our partition table aware of all the partitions which it has. So let's do the next thing here. What we want to do is, actually, we can do some queries here. For example, we can say, just to keep it simple, select star from this table which we just created. Oops, I think I loaded it again. Let's close it. OK, go back. OK, let's log in again. Awesome. So we are again in our terminal. I wanted to do a select star from the file, the table which we just created. OK. And let's do some limit 10. So we'll just see the top 10. And what it is going to do is it's going to the partitions, checking what kind of file it has. So it's giving us a consistent view across all the partitions. So it's we can apply like partition filters, and as you would imagine, those queries will be much faster than our normal queries, because if you say where date, the partition which we had here was sale date, and if that filter is applied, the query will be much faster because it's going to look at very small set of data. But if the filter is something outside of those partitions, it's going to look at all the data and think in terms of what different filters are applied and try to reduce the set of data. So let's so I just ran this query. Now one of the things we can do to understand how our partitioned tables is performing is we can create an external there's a table where we store this. It's called SVV external partitions. So let me run this query, and then I'll show you what this query is doing. Let's scroll down. So there are a few things I'm doing, saying select schema name, table name, values, location from SVV external partitions, where is schema name equal to spectrum_5. So this is the schema I just created. It's telling us what partitions this table is aware of right now. So it's telling for a given table, at a given time, you can ask what partitions exist. So it's telling us it probably has some 8 or 9 partitions. Actually, it's I think 12 partitions, and it's telling where each of the partition data resides. So that's good to know. Now we can do a query just to see how this table is performing. 1 minute. OK. Let's do a query here. So in this case, we did a similar query again. We are saying, tell me top 10 customers where the sale was greater than $30, and tell me the top 10 events. I'm not running timer here, but if you have a use case, you can imagine this query will be much faster than other, if you're hitting a partition. In this case, we are not. But if you apply a where a specific partition is being hit, the partition data queries will be much faster than others. And cool. So I think one more thing to understand here, there's another table which stores how S3 is performing for all the queries you're doing. As you become a more advanced Spectrum user, you would want to see how Spectrum is performing, like how many time I'm hitting S3, what kind of performance issues I'm having. So it's telling us for each query how much time S3 took. So it has like bunch of things, things like how much time was elapsed in S3, what was the table name, how many rows did we scan in S3, how many scanned bytes we had. One thing to remember here is Spectrum is an on-demand service, which means you don't pay any fees if you don't run a query. You pay only if you run a query. And the way query is charged is how much data it is scanning. So it's good to, when you have a use case which is repeating, it's good to check how much data are we scanning. Based on how much data you scan, your price will vary. And it's telling us how many rows were returned and a lot of other interesting things. So this is a very interesting query to be aware of if you want to check how my S3 interactions are happening, how much time it is taking, and other things. Now let's jump into the next piece. So far so good. It's doing partitions. Now I want to show you how do you automate all this. Like one of the things which a lot of people have is you have a lot of data coming in. how can you create a compressed file out of the raw data which is coming? How can you make sure it is Parquet or something else which is fast? How can you compress it? So let me show you how you can do it using Parquet. So we have a service called Glue. It does a lot of things for you, so I'm going to show you some of them. So first thing first, I want to show you a lab. This is just good to remember because for some of you who are interested in this, you can just repeat this lab in your home or in your office. This contains all the instructions of what I'm doing. So if you want to repeat this, just go to this link. Some of my colleagues have created this. It allows you to use Glue to create a serverless data pipeline or a ETL pipeline, which is taking the data and it's converting into Parquet, it's compressing it, and then all the things happen from there. So this is just a good thing to be aware of. Now let's move to our normal exercise. So first thing, I want to go to my console. I'll go to my AWS console. First thing, let's create a new S3 bucket. So this will be a bucket where I would put my data. So let's call it Anupam -reinvent. Let's say 17. Cool. And I'll say create. So I just created it. And within that file, within that bucket, I'll create two folders. One is a temporary folder, and one is a target folder, and I'll explain you why. So temporary folder is for temporary files, which Glue is going to create, and target is where I want my final data to come. So what Glue is going to do is, it's going to take the source data, it's going to run, it's a Spark engine actually, so it uses Spark to convert your raw data into a compressed data, which could be snappy or could be anything else. And it also does Parquet. Parquet is a columnar storage, so when you have a filters in your query, how many of you know about Parquet here? Just raise your hands if you know. Okay, probably half of you don't know. So I'll quickly tell you, there are a lot of columnar formats these days. Parquet is pretty popular, but there are a lot of others. But what they do is when you have a query where you say select column A, column B, column C, it's taking only those 3 columns. It's not looking at all the columns. So if you have very wide columns, columnar storage is very, very efficient. It saves a lot of money. It's also very fast. And compression, as usual, is great because you're scanning less amount of data if it is compressed. So I created these two. Now let me go to Glue, and we're going to do some cool stuff there. So Glue is a very new service. I think we GA'd it in last New York Summit a few months back. So first thing first, what I'll do is I'll add a new database. Let's call it. So for this use case, I'm using a taxi data. The reason I'm using taxi data is it's a pretty big size data, and a lot of things have already been done on that. So I just want to keep it simple and easy. So let's call it ny taxi data 5. That's my database name. So I created that. And what I will do there is, now first thing what I want to do is, there's a concept of crawler. So what crawler does is, you can tell a Glue crawler to go to a specific location and check what data exists there. And then whenever a new data file comes, it can automatically run a series of steps and do some ETL for you. So let me show you how it works. So first we have to give a crawler name. So let's call it reinvent 17. Next. So there are 2 types of data store it can go to. It could go to a JDBC connection, so it can go to there and say, hey, tell me what data you have, or it can go to a S3 location. And then, let's use S3 here. And then you can either crawl the data from your own account, a bucket in your account, or you can crawl from another account. So in this use case, I'm crawling from another account. There's a public bucket which is already created, so I'm going to use that bucket. So let me go to my notes. And there's a bucket which already has some New York taxi data. This is open source data which a lot of companies use for testings like this. So now it's asking, do I need another data store? I will say no. 1 minute, let me make sure there are no patterns. Cool, so I'm not using any patterns. And then IAM role, you can create a new role, or you can use an existing. I've already created a role, so I'll just use that. It's pretty simple. Now there are 2, 3 options here. Do you want to run it hourly, daily, weekly, monthly, or on demand? So to keep it simple, I'm running on demand. And then it's saying, what do I want to do with the output? So this crawler will do a bunch of things. It comes with a result. What do you want to do with the result? So it's telling, do you want to put it in a database? Yes, I think we just created, I think, second one? Yeah, okay, sorry, forgot. Prefix added to the tables. So when I create the tables here, so what it's going to do is it's going to discover the data. Once it finds it, it's going to put it in this database. Do we want to add a prefix to the table? Yes, we would love to. So let's call it reinvent maybe _17 _. So what I'm going to do is every table it creates, it will add this prefix. Next, it says, okay, finish it. Once we do that, this crawler is ready. It's saying, do you want to run it now? Yes, we will run it now. So it's running right now. I think it takes about 30, 40 seconds. So let it run. By the time it's running, let me show you the architecture of how this thing works. So a quick show of the architecture here. So, and let me make it a little bigger. So there's a S3 bucket, and S3 bucket has some data. This is the source data. It could come from your web servers. It could come from your third party, which are pushing data to you. It could be anything. So you're getting a lot of data. Once you get the data, Glue crawler will go there and discover what does this data look like. So it's going to interpret some things, but you can also override some of the things it interprets. You can say, okay, whenever you see this column, even though it's called ABC, I want to call it XYZ. So you can change those things. And then it creates a catalog based on that data. So it creates just the it's called catalog, which is metadata. So it knows what does the schema of this data look like. And then we run a job. Look at the bottommost thing here, the bottommost bucket. This is another bucket, or it could be same bucket. But what we are saying is that the source data will come in CSV format on the top. Crawler should go there every hour or every day or whatever frequency you choose, and it should take that data and put it in a Parquet format in the lower bucket. And once it is in lower, Redshift should use this data. Redshift should not talk to the source data. So because then you're compressing the data, it's Parquet, so it's fast. So everything, every good thing is happening by using Glue, and Redshift is talking to this. Redshift Spectrum is talking to this. So hopefully our job would have finished by now. Okay, so yep, it says done. So if you look at this crawler, what it does is, so I think the crawler was called reinvent 17, yep. So if we go to this, it says it added 3 tables. So now if we go to our tables, we should see some 3 tables. To make it simple, I think we added a prefix here. Let's refresh this. It's showing, okay, one of my, yeah. So when I refreshed, I think my new table showed up. I call them reinvent _17 whatever that is. So let's look at one of them. So let's go to yellow one. So it's saying that by looking at the data, it thought there's a vendor ID, which is, actually let me increase the font size here. It's saying there's a vendor ID, which is big int, there are a few other things like that. And then once we have that, so it has created a table. The next thing we can do is we can create a job. So what I will do is I'll go to the jobs here. So now it understands the table. Now let me quickly create a job. So I'll call it reinvent _park _job, let's call it. And then IAM role, I already have a role. Do I want to use a proposed script generated by AWS Glue? So we already have a lot of scripts. We'll use Glue script rather than writing our own, but we can always run our own. So you can have your custom code, which is Spark compatible Java code, and then you can put it here. But let's use the one which we have. And then saying what is the file name, that's okay. S3 path where script is stored. So we created a new table today. I think we called it reinvent something. So here it is. Okay, so I select that bucket. S3 path where script is stored. And then because this script doesn't exist, it's going to put its script there. Temporary directory, so this is where the temporary directory we created comes handy. So we'll say this is the temporary directory you can use. And advanced, by default job is disabled, so we're going to say enable, next. And then choose your data source. So we are saying what are the data sources you're interested in. So in this case, we're going to choose just the yellow taxi just to keep it simple. And then choose your data targets. So target could be an existing table or it could be a new table. So let's create a new table. We'll say, hey, we don't, every time you find a set of data, create a new file in S3, and the format of that should be Parquet. So as you can see, there are a bunch of formats we support: JSON, CSV, Avro, Parquet, and ORC. So for this one, we'll use Parquet. And we'll say, where should you store this file once you have done all the work? So we're going to say, store in the same folder, but store in target. So you can have a different bucket here if you want. And then finally, it's showing, do you want any customization on top of what I discovered? So it's saying there's a vendor ID, which is big int. So we can probably change some of the things if we want. Like we can call it pickup date can be called pickup underscore date, let's say. So you can clean up things. You can change data type if you want. So in interest of time, I'll keep it simple. And then finally, it's saying, do you want to run finish? And once we finish, it shows the code it has generated. So it is saying it has done, it's doing this mapping. It is doing some dynamic mapping. So this is the simple code. But as you can see, it's doing a lot of Spark jobs. And then finally, I'll run this. So once I run, for the data which I have chosen, it takes about 30 minutes. So I'm not going to ask you to wait here. I've already done it in a different database. But just to show you, the way you can use it is, let's go here. You can do a, so what this will do is the output of this will be, if you go to your S3 file, the bucket which we created, you will see glue. So this is one which I created earlier. If I go to target, you'll see things like this. So it will create a lot of snappy Parquet files. These are the files which it's creating based on the data which it discovered. And then you'll point your spectrum to this, and this spectrum will be much faster than what it would be on a raw table because it is columnar, it is compressed. Just to complete the story, let me just create this. I'll go back to my console. Okay, let me exit. Oops. Okay. Oops. Okay. So Control Z. Okay, so I already have, so I haven't created the schema, that's okay. So I think I can create it here. Okay, it created a schema, and then I'll just, so as you can see, this is a very similar command. We have done it like a bunch of times now. We are again creating an external table. We are just saying stored as Parquet. That is the only difference. We're telling that it's a Parquet data. It created an external table. The only difference you will see is this will be much faster table, much cheaper because the data is compressed, columnar storage, and you just got everything by clicking, bunch of clicks, like no scripting done. Everything is automated. You can schedule your jobs, you can queue them, you can do a lot of things. So that was the demo I wanted to show. We have like 5 minutes or so. So we're gonna use that for questions. I can quickly show you that this table indeed works. Just do a select count star on this. So it will probably show us there are probably a million or so, 10 million or so rows in this, and it's doing pretty fast. So that's the end of the demo. To summarize, what we did was we started with a file which was stored in S3. We queried it using Redshift. Then we created a Redshift native table. Then we combined both of them. And then finally, we showed once you have the files in S3, how can you use Glue to automatically create compressed files and columnar storage like Parquet or something else using Glue. And everything can be automated. So one of the frequent use cases I see is a lot of customers who have big clusters. They do a Redshift unload, which means they remove some data from Redshift, they put it in S3, and then they run Parquet on it, so it becomes fast. But still, they get a lot of cost advantages. They got a lot of performance advantages. So you can think about use cases where you can use it. With that, Mike, you want to come on the stage? Let's take a couple of questions. If you have any questions, we would love to answer them. Yep.
So, quick question: when you're scanning flat files with Spectrum, large data sets, there's going to be some bad data, right? So when the samples for that data, or just with the raw results?
Yeah, so if there are like anomalies, let's say there's things which don't match, there's some way for you to say ignore it. So for example, you need to come up with a fallback, right? If the column doesn't exist, to put a null there or things like, it's a relational database, so you can do all that. But you just need to be aware what is the fallback you're going to, because some people are very strict that I always want this column, for example, if it's an identity column or things like that. But if there are some mismatches, you need to decide what do you want to do when a mismatch happens. Because you have the full access to the script, it will be mostly customization through the script, the Spark script which we have in the glue. So it auto-generates the base script for you. In most cases, you don't need to change it, but if you know there are data quality issues, you will have access to each row there. You can, like, say, do some custom things on top of it. Yep.
When you're doing the partitioning, the sales date in this particular example, was the name of the directory importance, the sales date equals, or is that just the directory name for convenience? The sales date itself wasn't in the file, was it?
So sales data was in the file, but the name, the path is very important there. That's how it knows which files to go to. So when you say partitions, you can have like a high number of what is called slash delimited values, and it will go first partition, second partition, third partition. So the format is partition name equal to, partition name comes first, equal to what is the value of that partition for the data which is stored within that folder. Yeah, that's required, yep, as far as I know, yep.
I have a question on the group. When you create a table, it's not to be after you create the Parquet file.
Yep.
So you said this partition and concurrency, but we are not mentioning the partition here. So how,
The New York taxi which we created. Yeah, so in this case, it's not partitioned. So if you go to the source data, I can quickly show you. There's no partition there. It's compressed and Parquet. So there are three things here. One is partitioning, which means you have a logical structure to your files. We are not doing that in the last step. We are doing two other things, though. We are compressing it using snappy compression, and we are also using Parquet. If you open the file, it will look like it's a binary file. We cannot, like, there are ways to read Parquet, but you cannot directly read it. So partition is not happening here. It's Parquet format, and it's compressed. What? Oh yeah, actually we should. In the interest of time, I didn't do that, but you can have a step where you say, you should put the file in the partition name. So, yep, so that will kill two birds in one shot, right? Yeah, awesome, yep.
Performance question about sort keys and traditional sort keys. I guess we're not supposed to compress the initial or the first column in the sort key. Does that also apply to in compound sort keys? Does it also apply to the other columns in the sort key? And also, how does that apply to the interleaved sort keys? What's the best practice on compression?
Compression of sort keys. Yeah, do you know about that?
Not for the compound interleaved.
Yeah, because I know the primary key shouldn't be compressed, but I don't know about this from the top of the head, so we'll discuss offline and see if we can find an answer. Yep.
is Spectrum based on Hive syntax?
Is it Hive syntax? So Spectrum is, when you use Spectrum from Redshift, it's exactly like Redshift. So you don't have to decide, oh, it's Spectrum, so my query should be different. Your interface to Spectrum is exactly same as Redshift. That's the best benefit, actually, because there's another option called Athena, which we didn't go to today. But you can query S3 files using Athena as well. But the advantages of doing through Redshift is if you have existing data in Redshift, you can join very easily. It's very seamless to your user experience because the queries will automatically go to S3 or Redshift depending on where it is stored. But the way people are interacting is going to be same. Yeah, let's take one last question.
If I want to unload all the data from Redshift to S3, like example, order verified yes, maybe, should I consider this design and create separate tables for each year to unload this?
Yeah, so that's a good question. Like if you have a lot of data in Redshift, how should you unload? The best way people do it is you think, look at your query patterns and see how much of data you generally scan. Like look at your daily query patterns And if you think that more than 2 years, like older than 2 years is never queried, I think it's a good idea to put that in S3 because the performance of data in S3 would not be same as this, but it's much more scalable. You can have like exabytes of data and still fire a query with a very low cost. So what people do is they generally have time data, yeah. So the table will have some time component in it. It could be year, it could be month, and then they have a rolling window kind of thing, like keep your last 12 months in Redshift, and everything older retires to S3, and then you add a new partition in the file, so you have like access to both of them. Yep. Cool. So we'll be here, and we'll take some questions offline. But thank you very much for coming here.